Welcome to this video on censoring and truncation. Censoring and truncation is a classical topic in econometrics, and I will give you a glimpse into what this actually means. Now let's first define things. So censoring means that when I have a regression equation, say y is x beta plus epsilon, the outcome will actually only be observed if it takes uncertain values. So I will always observe the covariates, but the outcome will not be observed. So an example is hours worked are only observed for working women, and the characteristics would be observed for all women. Or I could have a case of censoring when income is not recorded if it is above a certain threshold value, but I would still know that it is above that value, and I would still observe characteristics of individuals. Truncation is very much related to that. Truncation means that outcome and covariates are only observed if the outcome takes uncertain values. So the sample would only consist of working women here, or the sample would only consist of people for whom income is below the threshold above which it is not recorded. All this is closely linked to something that is called sample selection. Sample selection means that the sample that we have is not representative of the whole population. So an example here is that the sample of working women is not representative for the population of all women. Now, I've split this into two parts. The first part covers very classical material. So this is the so-called Tobit model, and we're going to look at the type 1 and the type 2 Tobit model. And in the second part, we're going to look at some generalizations. What is the type 1 Tobit model? So the type 1 Tobit model has as the starting point that we're interested in explaining continuous variation in a dependent variable that is restricted. In early textbooks, oftentimes people have talked about expenditures that cannot be negative, hours worked that we just talked about, that are only observed if individuals work for some hours, and so on. The aim here is to have an econometric model that does account for this. So an econometric model that is more general than the linear regression model, y is x beta plus epsilon, that can take this into account. And already in 1958, which is quite a while ago, James Tobin proposed a, I quote here, hybrid of probit analysis, which would explain whether the outcome is observed, and multiple regression, which would explain variation in the outcome if it is observed. How does the baseline type 1 Tobit model look like? We would have a latent dependent variable, or latent variable yi star, that is xi beta plus epsilon I. So this is very much like the latent variable that we have seen earlier in this course in the ordered choice model. We would have an epsilon, that is the econometric error term, that is normally distributed with mean 0. That's the location normalization. But now we don't need a scale normalization, actually. We have a free parameter, and that would be the variance of that normal distribution. Now, censoring means for this model that yi is observed, so yi star is observed as yi if it is bigger than 0, for instance. can be also bigger than other values. You can think of other observation rules, if it is in a certain interval, etc., etc. That is not essential here. So here it's written down for the case that yi star is observed as yi if yi star is bigger than 0, which is written down here. And this is called a model for censoring from below at 0. Truncation would mean that yi is observed if it exceeds 0. So yi is equal to yi star if yi star is equal to 0. So notice the difference again that I talked about earlier. If yi star is bigger than 0, then it would be observed as yi in both cases. In the case of censoring, we also have cases where yi would be equal to 0. So we would know that for certain x's, the observation has been censored. Whereas for truncation, we would not know about this because these observations wouldn't be in our data. Throughout, we're interested in the dependence of this latent variable on x's. So that is summarized by the parameter vector beta. And the first thing we can now do is we can pretty much, in parallel to actually writing down a probability for a Probit model, figure out what the censoring probability actually is. So that would be, formally speaking, the probability that y is equal to 0 given x. That is the probability that xi beta plus epsilon I is less than or equal than 0. And that would be the probability that epsilon is less than or equal than minus xi beta when I bring xi beta to the other side. So what we do see is that when xi beta is increasing, then this probability will decrease. And the intuition for that is that when I have a very high value of xi beta, then I need a very, very negative draw of epsilon so that the sum of the two will be pushed below 0 so that censoring occurs. Okay, so this is behind this statement here that is decreasing in xi beta. Now we can make use of the normality assumption that we've made. So we can write this as follows. So it will be the probability that, and this is actually a nice link also to our earlier discussions, in particular about the Probit model. And in the context of the Probit model, we have talked about this scale normalization, right? That when we compare a Probit model with a variance of 1 to a Probit model with a variance of 4, that coefficient estimates will be rescaled. So technically, we now do something that is similar to what we have done there. So we're figuring out how we can write that censoring probability in terms of the CDF of the standard normal distribution. And what you see is, as we did it earlier, we have to now write down the probability that epsilon I divided by sigma, which is a standard deviation of our normal distribution, is less than or equal than minus xi beta divided by sigma. So here we have these rescaled coefficients appear again, and that random variable here, epsilon I divided by sigma, is now a standard normally distributed random variable, so we can use the standard normal CDF. So what we get is that the censoring probability is the CDF of the standard normal distribution evaluated at minus xi beta divided by sigma. So what we see is when xi beta is increasing, that argument becomes more negative, and the CDF evaluated at something relatively negative, that is relatively big and negative, will be very close to 0. So that means, indeed, when I increase xi beta, that argument will become more negative, so the censoring probability will actually decrease. Now I can also do something on top of that. I can rewrite this, and I can say, okay, by the symmetry of the standard normal CDF, we can also write down the probability that the observation is not censored. So that would be the probability that epsilon divided by sigma is actually bigger than minus xi beta. That would be 1 minus the probability that it's smaller, so which is what I've just derived here. And then by the symmetry of the standard normal CDF, we have 1 minus the standard normal CDF evaluated at minus xi beta divided by sigma equal to the CDF of the standard normal distribution evaluated at xi beta divided by sigma. So this is what we have actually seen also before when we talked about the Tobit model. And in the context also of seeing the Tobit model as a special case of the ordered Tobit model. Now let's think about what's going wrong when we ignore censoring and truncation. Earlier we already said that we can use OLS whenever the expectation of our outcome in our data given x is equal to xi beta. Now let's see whether that holds, when that holds approximately, and when it doesn't. So let's just write down that expectation for the model we have here for the type 1 Tobit model. So the expectation of the outcome given x would be, well, now I split it up into two parts. The probability that the outcome is 0, so that I have censoring, and then I have a 0 in my data, plus the probability that the outcome is not censored given x, and then I would have times the expectation of the outcome given x and given that it is not censored. So this holds by definition. There is no assumption necessary. I can just write that down. I can always split up an expectation like this. Now, by the way, the 0 is just one way of, it's the natural way of coding censoring in the data. Okay, so in principle, one can make other choices, but here I've kept it, I've left it at that. So this is the standard way of coding the data. So it would be 0, or actually, when it's not censored, the value that yi star takes on would be observed as yi. Now, because it's coded as 0, this first part will vanish. So we're left with the second part. I'm just leaving that probability here, and I'm writing out what that expectation of the outcome is given that it is not censored. So it would be the expectation of x beta plus epsilon given x and given that there's no censoring. So that's the sum of two parts. Given x beta is equal to x beta. So that is this one here. Plus what then remains is the expectation of the econometric error term, the epsilon I given x, and given that there is no censoring. And given that there is no censoring means that epsilon is not too negative. So epsilon I, as we have seen before, epsilon I needs to exceed minus xi beta. Now, in general, this stuff here is not equal to xi beta. Okay, so for that reason, we can already see that we can't just run OLS and trust that everything will be fine. What we do know actually is that the expectation of epsilon given x, and given that epsilon is bigger than something, is always bigger than the expectation of epsilon given x, which is what we would have in the case without censoring. And that one here, the expectation of epsilon given x is at least implicitly assumed to be 0 up here. So we would always have that this one here is bigger than that. So for that reason, we can't, for that reason in general, the expectation of y given x is not equal to xi beta, and therefore a regression of y on x yields biased estimates. And a similar thing holds for truncation. So in the case of truncation, what we do have is that the expectation of y given x, and given that y is a positive, is also equal to x beta plus the expectation of epsilon given x, and given that epsilon is exceeding minus xi beta. The one difference is here that here I have in addition this probability, right, in front of the expression. Otherwise, this expression here is the exact same expression as this expression here. Okay, so and this one here is always bigger than xi beta. So also here, in general, a regression of y on x yields biased estimates. Now, that's a very abstract way of reasoning. The question is, how bad is it, right? What you can probably already see when you look at those formulas here a little bit is that the problem is probably not too big if the censoring probability is relatively small, right? It will probably approximately hold in either case that the expectation of y given x is about approximately equal to xi beta if that probability is relatively small. But that's a somewhat more refined statement, and we will have to see in practice how this works out. What you can see from this slide here is that when you say plot the data and you know that we have say censoring from below at 0, and basically all your observations are pretty much away from 0, that this probability is probably very small, and for that reason you should probably not too worried. Or you have some prior that censoring will basically not really happen in your case, then you can move on, then you're fine. But that is something you have to look into in a particular situation. So that is not something one can say in general. What one can say in general is that running OLS will, well, not be fine. Good. So how does then the type 1 Tobit model approach all this? So I like to present the type 1 Tobit model here for two reasons. One, it makes us aware of this potential problem, and maybe once we understand the problem, we can actually see that in our particular application this is not too big a deal, right? The second reason why I like this model is because it teaches us a little bit more about how we can construct models so that the observation rules that generate the data are taken into account in the estimation step. So looking into the way this is being done here can maybe teach us a little something about other situations in which we may want to put together a model that takes into account a particular way in which the data have been sampled, right? So against that backdrop, let's look at the type 1 Tobit model. In order to do that, let's define an indicator di that is equal to 1 if yi star is being observed. We have already shown that the censoring probability is this one here. So it's the probability that yi is actually equal to 0 given x. That was the standard normal CDF evaluated at minus xi beta divided by sigma, where sigma is the standard deviation of this normal distribution. Beta and sigma are both parameters that we wish to estimate in the end of the day. So that's one part, one building block that we'll need. And the second one is the density of yi star. We can always think about this, no matter whether it's observed or not. So we can just write down what the density is. So we do know that yi star is normally distributed with mean xi beta and variance sigma square. So in order to use the density function of the standard normal distribution, what we have to do is we have to take the CDF of the standard normal distribution and evaluate it at yi star minus xi beta. So we have to take out the mean and we have to divide by sigma. So taking this as the starting point, we can take the derivative of that expression with respect to yi star, and the derivative of a CDF is going to be a density, and that gives us the density here. So it's the density of the standard normal distribution evaluated at yi star minus xi beta divided by sigma, and in front of it we have a 1 over sigma. So that gives us exactly what we need. Now, let's work our way towards writing down a likelihood function. So when we have censoring, then we can write the density of yi given xi and di. Di was our indicator for yi being observed or not being censored as follows. So this is just how I denote this. If I have censoring, then the likelihood contribution is the probability that there is censoring. This standard normal CDF that we have seen before. And if there's no censoring, then it's the density of yi star. This can in turn be rewritten as one expression where I simply use that CDF to the power 1 minus di. So when di is equal to 0, then it will pick this part of the density, and this part here will be equal to 1, because something to the power 0 will be 1, so it will pick this part. And conversely, if di is equal to 1, this first part will be 0, and only the second part will remain. And the log likelihood function is then simply the log of this whole expression and then summed up over all observations. I. Now, for truncation, it looks similar. So what we need to do now is to look at the joint density of yi and di equal to 1. That is this density that we have seen before. This is just the density of yi star that we have derived earlier. We have also derived earlier what the probability is that yi is observed. So this was the CDF of the standard normal distribution evaluated at xi beta divided by sigma. And then we can simply apply Bayes' rule to get the density of yi in the truncated sample. So that would be the density of yi conditional on di is equal to 1. So I'm getting this joint density in the numerator, and in the denominator I do get that probability that yi is not censored. So this will be my likelihood contribution. And this already concludes the discussion of the type 1 Tobit model. As I said, very classical material that I think you should see once, also because it nicely links up to earlier discussions we had, in particular in the context of the Tobit model. There's an extension to the type 1 Tobit model, which is the type 2 Tobit model. Actually, there are multiple extensions. I'm just going to talk about the type 2 Tobit model as the only extension. The type 5 Tobit model is particularly close to what is now a hot area, which is program evaluation. That will be discussed in the second half of this course, but I'm not going to talk about this now. I have a little something on this in the lecture notes, actually. So in the type 1 Tobit model, the probability to observe yi, to have an uncensored observation, is this CDF of the standard normal distribution evaluated at xi beta divided by sigma. And then once one observes the outcome, the dependence on x is also basically governed by this parameter beta. And this is restrictive because x influences in exactly the same way whether an observation is censored, and then when it is not, how it depends on x. So when you look at the female labor supply example that people have cited quite a bit in the literature, then it's usually argued that this is restrictive because it imposes that the same variables that explain whether a woman works also explain how many hours she desires to work. And also that the relative importance of these variables is assumed to be the same. And the type 2 Tobit model relaxes this assumption. So it's really just, in some sense, conceptually very clear what is being done. We just split this up into two parts. Okay, so we have a separate binary choice model, and that will determine whether or not there is censoring. And then we have another part of the model that will describe the relationship between the uncensored variable and x once we observe it. So towards putting this together, let's define an indicator y1i that tells us whether the outcome of interest is observed. Okay, so this corresponds to the di that we had before. Then there's a latent index, y1i star, which is given by x1i beta 1 plus epsilon 1i. And the binary choice model that tells us whether or not there is censoring is as follows. y1i is 1 if y1i star is positive. So that actually is not directly like the formulation that we've used in the context of the binary choice model, but more closely related to the formulation that we had in the ordered choice case, in the ordered choice special case with basically two alternatives. So also there we had the sum of the two entering the y star, and we had like the alternative number 2 was chosen if y star was positive. But then I also showed you in which sense this is observationally equivalent or has the same empirical content as the binary choice model as we've discussed it in the very beginning. Now, in any case, so this is the part of the model that tells us whether there is censoring. So observe that we have here the x1i, and we have a parameter, a vector beta 1. And on top of that, there's a second latent index, and that would be called in this example the desired hours a woman likes to work. And that would be y2i star, and is given by x2i beta 2 plus epsilon 2, and we observe y2i star as y2i if y1i is equal to 1. That is how the model works. And now comes, say, the fun part. The fun part is that there are now two error terms, of course, in this model, epsilon 1i and epsilon 2i. So epsilon 1i is part of the binary choice part of the model. Epsilon 2i is in the part of the model where we say what the hours would be if they're observed. So what we assume is that they're bivariate normal. The mean for both would be assumed to be 0. But then for the variance-covariance matrix, what we do is we impose a scale normalization for the error term in the binary choice part of the model. But then we have on top of that, we have a variance parameter for the continuous part of the model and a covariance parameter. And the covariance parameter is kind of fun to think about a little bit. That covariance will capture a dependence between the epsilon in the hours equation and the epsilon in the participation equation. And in the type 1 Tobit model, that correlation was 1 because we only had one epsilon that entered both parts of the model. So in that sense here, we have a more general structure where we have more or less dependence. We can also obtain back the type 1 Tobit model as a special case. So what we have to do for that is to, of course, impose that the x's are the same, the betas are the same, and that epsilon 1i is equal to epsilon 2i. And then what we have is that the variance would be epsilon 2 square. So this actually brings us to a point that you might have been wondering about when I talked about the type 1 Tobit model. Why can I actually estimate that variance? Well, I can estimate that variance from the uncensored observations, right? So the type 1 Tobit model only had one error term, and when I have an x for which basically all observations are observed, then what I can simply do is I can look at the variance of y, and that will be the variance of epsilon. So that tells you why this is actually identified. Once I have two error terms in the type 2 Tobit model, I need to do what I did here, namely to impose a scale normalization as I did in the usual binary choice model earlier in this course. And there's nothing wrong with imposing a normalization. It just means that otherwise the model is too general. Something that has become famous in the late 70s was the and later on was the so-called Heckman correction. So the Heckman correction goes like this. The Heckman correction is starting with writing down the expectation of y2i given the x's and given that an observation is not censored. So given that, an observation is not censored if x1i beta 1 plus epsilon 1 I is positive. So I can just rewrite it like this. This is this first equality. And the second equality then substitutes in the functional form for y2i. So given x2i, this is going to be x2i beta 2 plus then the expectation of epsilon 2i given that the observation is not censored. And here comes the big insight that Heckman had. The insight was that bivariate normality actually implies that the expectation of epsilon 2i given that epsilon 1i is bigger than minus x1i beta 1 has a closed form, and that closed form would be the covariance between epsilon 1 and epsilon 2 times this function lambda evaluated at x1i beta 1, and this function is called the inverse Mills ratio. That's a result from statistics, and the inverse Mills ratio is the density of the normal distribution evaluated at x1i beta 1 divided by the CDF of the standard normal distribution evaluated at x1i beta 1. And given all this, the way this works is that we do a two-step procedure. And as I said, this two-step procedure is attributed to Heckman and did certainly contribute to him getting the Nobel Prize in the early 2000s. So what one does is one first estimates a probit model with all observations. So the censored and the uncensored observations, and that probit model explains whether an observation is censored. Once one has done that, one has an estimate of beta 1, so one can calculate the inverse Mills ratio for all observations. So that would be here denoted by lambda hat, and that is simply that lambda function, which is the density of the standard normal distribution divided by the CDF of the standard normal distribution evaluated at the fitted value of the part of the index of that binary choice model that has nothing to do with epsilon. Okay, so it's x1i in the data, beta 1 hat. And what one can then do in the second step is to estimate a model in which one regresses y2i, the outcome that is observed when an observation is not censored, on x2i and that fitted value of the Mills ratio term. And that will give us consistent estimates of beta 2, because the expectation of this remaining error term is going to be 0 conditional on x2i and conditional on that Mills ratio term. Okay, so that's why this works. The mistake that we would be making by running a regression of y2i on x2i is captured by this by including this additional variable. So this can be thought of as being an omitted variable. So if we omit it, we make a mistake, and then we get a bias due to censoring. But if we include it, then we get consistent estimates of beta 2. Now, and notice that by doing that, we can actually estimate the covariance between the two epsilons, and that has a meaning then again, right? So that is also interesting, just as an aside. Good, some important points. So it's a two-step procedure, and it turns out that the error term is heteroscedastic. The variance of the error term here will depend on x. So this whole procedure is inefficient in the way I've described it here. Second, we need to correct the standard errors because we have a generated regressor here. So the lambda hat is actually estimated in the first step, so we can't just ignore that. However, this is not necessary when we do a test for selection. So a test for selection would be a test for sigma 1, 2 being different from 0. So if it is equal to 0, then we actually have no selection, right? So if the null hypothesis is that is equal to 0, under the null, the usual standard errors are correct. They're just not correct under the alternative. So if we want to test for selection by, in the end of the day, doing a t-test, we can use the usual standard errors. Finally, practical point. So when you plot the Mills ratio, then you will actually see that it's most of the time very close to being linear in its argument. What really helps here is if x1i and x2i are different from one another, which is very close to actually having an instrument in the so-called selection equation. So the selection equation is the equation that tells us whether or not there is censoring. We're getting close to what is being discussed nowadays in the program evaluation literature, and also there it often helps to actually have an instrument in the sense that x2i is not equal to x1i. Good. So this already ends the first part of this video on censoring and truncation. In the second part, I want to talk about a little bit of material that's related to generalizations. The general gist will be that actually parametric models work relatively well, and this parallels a little bit the discussion we've had before in the context of binary choice models, where we've also seen that the Tobit model, as compared to the Klein and Spady estimator, for instance, did relatively well. And what I want to look at here in particular is a paper by Bertrand Melenberg and Arthur van Soest, my colleagues here in Tilburg, from 1996, where they relate the share of the budget that families spend on vacation to family income, household composition, and other family characteristics. This very much fits into censoring and truncation, because the budget share is 0 for a substantial number of Dutch families, about 40%. And what they do is they estimate two types of models, and this parallels what we've seen earlier, type 1 Tobit, type 2 Tobit. So several parametric and semiparametric extensions of the single equation censored regression model, type 1 Tobit, and two equation models in which participation decisions and the amount spent are treated separately, which is the type 2 Tobit model. The general structure is more or less what we have discussed. Here I'm translating it into their notation. So there's a latent variable. So now we have the single equation models first. There's a latent variable yi star, which is given by this expression here, and yi is either 0 when we have censoring, or when yi star is bigger than 0, then we observe yi star. So you can write this using the max operator. So yi is equal to the max of yi star and 0. The variables they use in their analysis are the following. So the first x is equal to 1. So the coefficient on that will be the constant term. x2i is the log of total expenditures. x3i is the log of family size. x4i is the age class. x5i is education level. x6i is the degree of urbanization, where they live. And x7i is the square of x2i, so the log of total expenditures squared. For the Tobit model, and this is actually interesting for you to see, they allow for heteroscedasticity, so they allow for the variance of epsilon to actually depend on x. So it's an extension to what we have seen before, where we have actually assumed that epsilon I had the same variance, and that across for all observations, and that variance was basically sigma square. Good. So let's look at what they have. So this is table 1. specification 1 here is the Tobit model. Then we have specification 2. We have some heteroscedasticity. Then specification 3, we have some random coefficients, and specification 4, we have again heteroscedasticity. I don't want to go here into the details what this all means. You have heard before what random coefficients are. You know what heteroscedasticity is, but again, I don't want to go into the details here. What I would like you to do is to observe that we have alphas here and we have betas. So the alphas tell us something about the dependence of our y on our x. So that would be the beta parameter that we have seen before, actually, in the type 1 Tobit model. And you can just look at this across specifications here, okay? Not understanding fully what specification 2, 3, and 4 are. What we have for specification 2, 3, and 4 here is a dependence of the variance of epsilon on x, so a specification for heteroscedasticity. So this is covered, captured by these parameters that are called beta here. Not going into the details, as I said, my reading of this table is that if we're really interested in these alphas, which have been denoted before by beta in the type 1 Tobit model, then it looks to me at least as if these coefficient estimates are somewhat comparable across specifications, in particular if one takes into account the standard errors, right? Always take the point estimate and then construct in your head a confidence interval around it. So you take these 0.22 and add 2 times 0.06 and subtract 2 times 0.06 and do this for this, and this number as well. Then you will see that to a large extent these confidence intervals are actually overlapping. Even here, when we get a point estimate of 50 and 92, notice that the standard errors are actually relatively big, right? So this confidence interval here will reach almost, will actually include this 50 number here. So in that sense, we don't get substantially very different results when we estimate more general models allowing for heteroscedasticity, at least not with these data. The next thing they do is they do something that is related to what we have seen before for the binary choice model. There we have looked at Mansky's maximum score estimator. So there we had this assumption that epsilon had a median of 0 independent of x, and one can actually also use such an approach here in the case of censoring, as described by the type 1 Tobit model, but then without making a distributional assumption for epsilon. Just making that one assumption that epsilon has a 0 median conditional on x. And this is then called censoring, censored least absolute deviations estimation, proposed by Powell. And there's an optimally weighted version of that, and that was proposed by Newey and Powell 6 years later. So this was proposed originally in 1984, and then the follow-up was in 1990. The way this works in a nutshell is that one minimizes the average absolute deviation between yi and what is predicted. And what is predicted is the max of 0 and xi alpha. Okay? You might wonder what this absolute average absolute deviation actually is. So think of it like this. For a candidate parameter vector alpha, for each observation you will calculate the max of 0 and xi prime alpha, and then you take the difference between the absolute value of the difference between yi and what you've just calculated, and then you just take the average over observations, and what this will do is it will give you a criterion function that you can minimize. And when you do that, then you're not trying to fit the mean, you're trying to fit the median for a given x, and that will work out, it turns out. So I'm being brief here. There is not enough time to cover this in more detail, but I hope you get the main idea. So here you see what we get in terms of results. There are certain choices that need to be made for tuning parameters. Again, I don't want to go into details. What I would like you to take away is that these numbers here are actually not too different from the numbers we have seen before. When I look at alpha 3, I get an estimate of 0.23 with a standard error of 0.9. And when I just go back here, then we had values that were somewhere in this range. The common element is that they're all fairly imprecisely estimated. So again, the confidence intervals will actually be largely overlapping. Below, without again going into details, you see the new power version that has some efficiency properties on top of the flexibility that comes from not making distributional assumptions other than this median restriction. There's an interesting table now, table 3. When you look at implied elasticities from this model, then what you will see is that they're actually very, very similar across specifications, across models that one estimates. And what I find interesting is that they are very similar to the elasticities that the Tobit model implies. And just to be precise, this is the elasticity of vacation expenditures with respect to income. So when I increase income by 1%, by how many percent will vacation expenditures increase? And that parameter is probably the most interesting one from a policy perspective. Good. And finally, what they do is they look into two equation models. They have a flexible selection part of the model, like corresponding to the binary choice part in a type 2 Tobit model. So in table 4, they look at a probit model, and then also at Klein and Spady estimates. And then what they do is they calculate the Mills ratio term and specify the expectation of epsilon given x and given that the observation is not censored as a flexible function in that Mills ratio term. And this can be seen as a generalization of the Heckman correction. And sometimes what people have called this also is a control function. So this Mills ratio, this function in the Mills ratio is called a control function, trying to capture the omitted variable in the model, in the sense that it was omitted when we did the Heckman correction. Good, so this then gives results that are reported in table 5. So we have OLS results that will be in column 1, weighted least squares in 2 and 3, and in column 3 we also have the Mills ratio term included. So first of all, the binary choice part of the model. Again, Probit model here, and this is Klein and Spady. They use as the scale normalization that the coefficient on the log of total expenditure is equal to 1, and not completely surprisingly, I would say these estimates, these sets of estimates are very similar to those sets of estimates when they use a different smoothing parameter for the semiparametric part of the model that we have seen before when we actually talked about generalizations to the binary choice model. This was this bandwidth parameter. Then they get slightly different estimates. But then again, for instance, the coefficient on the degree of urbanization here is very similar across these models. They get slightly different results for some other ones, but qualitatively at least, the results are not too different. And finally, here we have table 5. So this is the outcome equation that is of interest. OLS, weighted least squares, and then the whole thing with the Mills ratio in it. Yeah, again, when you look at just coefficients and you compare them across columns, then they're not terribly different from one another. And when they're different, then also standard errors are actually quite big. There is no alarming signal coming from these results, I would argue, that tells us that we really have to go semi-parametric or very flexible. So at least my interpretation of these results is that parametric models actually work quite well, and that type 1 and type 2 Tobit model results are relatively trustworthy, at least from what we can see here. Good. The final things I wanted to talk about were exam preparation. So what I would advise you to do is to start with the videos and the slides, and that you try to make sure that you fully understand every single detail on these slides. So the videos should be quite helpful for that, but do make sure that you do understand what is on those slides. Then you can go to the lecture notes. You can look at derivations. You can look at the text there. You can look for additional details. Also, I would recommend reading the first 2 sections just for some more general background information. And once you have done that, you should be in pretty good shape. However, to prepare for the exam, I would still advise you to look at the problem sets and make sure that you understand what's going on there. So everything on there is also fully relevant for the exam. And then finally, digest and reflect. And I hope then the exam will be a good experience for you. Finally, my last 3 points. So the first one is that, as I told you in the very beginning, I think most of economics nowadays is empirical, not econometric theory and not economic theory. So keep that in mind when you make choices, and keep in mind that also when you work on applied theory questions, some empirical analysis will always help you to make your point. Now, second point, when it comes to empirical analysis, in my view, that should be closely related to theory, and that should be guided by theory. It helps us tremendously to have a framework that we can use to interpret empirical results. And just think of McFadden 1974. We can use theory to make more of our empirical observations and to learn more from our data. When we have a good framework that we can bring to the data, we can use it to make predictions based on that framework and to say something about quantities that are only well defined within such a framework, such as welfare, and that is defined as the compensating variation in exactly the way we've talked about it. Finally, whether structural models or reduced form analysis should be used, in my view, really depends on the purpose of the analysis and on the data that are available and on many, many other factors. And this has already been pointed out in 1953 by Marshak. Here I'm giving you the citations. It's a great read, and it's actually available on the web. So, this brings me to the end of this series of videos. I do hope that you enjoyed watching them and that you've learned a bunch from these videos. And I wish you all the best for your empirical endeavors, and stay curious and have fun doing great work.